So now let's finally bring our discussion on black holes. What are they? What's their relationship to relativity? And what can we do with them? So, relativity describes the universe, the fabric of existence, as this space-time. And for our pictures, we generally think of it as these 2D plots, where if you plop a planet or a star in there, it curves the space-time. Well, a black hole is just the natural extreme of this. Take this to extreme. Make this thing more massive and more massive. The bigger the mass, the greater the dip, the bend, the change in curvature of space-time. And so if you go to the extreme limits, you get yourself a black hole. Get yourself something that's so mass and so dense that space-time literally plummets down to a singular point. We call that the singularity. And that's our black hole. Why do we call it a black hole? Well, it deals with the ability of light to escape it. So, one quick misconception that I need to lay out here. Black holes are not these voluminous objects that are just gobbling up, sucking the entire universe into them. In fact, we'll see in later videos how black holes can have objects in orbit around them. So you have to define a event horizon, and that event horizon is this cross-old threshold. If you cross the event horizon, you plummet down. We'll talk about more of that later. And if you're outside the event horizon, the black hole isn't this thing that's just gobbling, sucking matter up. It's just a massive body. And you can find examples of matter, stars in orbit around black holes. Heck, supermassive black holes exist in the center of basically every galaxy. They're helping hold galaxies together. So please, do not think of black holes as these sinks that just fill all the void of space and everything falls into them. No. They're just things that became massive enough that space-time collapsed to singularity. It does not mean everything is being sucked into them. So, some ways to make a black hole. Well, you have a supernova, right? You've got that violent collapse of the core of this supermassive star, and it's so extreme that the core itself continues collapsing in on itself, and that becomes the black hole. Or another example is you've got yourself two star systems, and you've got a neutron star. That means there's that neutron core left over from supernova, and its companion star starts dumping more mass on it. Instead of going nova again, instead of exploding, because fusion can't trigger again, what ends up happening is that neutron star collapses down. And that's what we have pictures like this. Adding mass onto it, till finally there's just so much that it just collapses everything to that singular point. Right. So we can talk about what's the surface gravity, right? On Earth, we say our surface gravity is 9.8 meters per second squared. Well, that's what I mean by the surface gravity on the surface of this neutron star becoming a black hole. As more and more material gets dumped on it, the surface gravity keeps going up and up. And an interesting characteristic of this, that warping of space-time, it's not just matter getting stretched out. It's light. The path of light near black holes starts to do some strange things. Remember, something as massive as the sun can completely deflect a ray. Right? Stars can deflect ray paths. Black holes can literally trap the rays. So you have your neutron star before it's gone dense enough, but shrink its volume down, start to become more and more like a black hole, and literally space-time itself will curve in a way such that light rays come out and whip around. And you can do some really crazy thought experiments like this, of say, shine a laser this way and watch it bend around the massive object and hit you in the back of the head. You can do some really weird stuff of light orbiting around a black hole. So, let's start to work our way towards this proper definition of black hole, not just this singular point in space-time. Remember, surface gravity, that defines what we call the escape velocity. I hope you guys remember that. You've been in this course for a while now. But if you don't, remember that surface escape velocity is how fast you need to move to get off of planets. To get off Earth's surface, we need to be moving something like 11 kilometers a second. We need to go very rapidly. And so you can calculate the escape velocity. Heck, even Newton's laws will get this. You just do square root 2 times gravitational constant, how massive the object is, and your distance away from it. Well, relativity says, hey, c is the ultimate speed limit. You can't go faster than light. And so if you set the escape speed at the speed of light, you get what's defined as the radius of the black hole, also known as the event horizon. So if you are outside that event horizon, your escape speed is less than the speed of light. You can escape. You can fly away if you have enough energy. But if you're at the threshold of the event horizon, in order to escape the gravitational well of the black hole, you need to be moving at the speed of light, at that critical level. If you take a half step out, you can escape. You take a half step in, and there is nothing in the universe that can save you. No way of escaping that black hole's gravitational well. So if your radius is less than the radius of the event horizon, your escape speed is greater than the speed of light, laws of physics say you cannot beat that speed limit. And I know I can hear the questions coming of like, but so-and-so says we can do this. These ideas of violating speed of light and stuff. We'll save discussions like that for future times, but for now, that's all speculation. The speed of light is a universal speed limit. Nothing has broken that in nearly a century's worth of experiments. 2 centuries, getting up there. And until we break that speed limit, you're going to have to do a lot of work to convince me you could fly out of a black hole. So, a formal name for that event horizon, it's going to be called the Schwarzschild Radius. Right? And the Schwarzschild Radius is that point of no return. If you are a distance less than this away from a black hole that's this massive, you can't escape. So some interesting consequences of this. A black hole used to be a star, or at least remnants of a star, collapsed down to a singularity. It still has some mass. Think about that. Think about something that's orders of magnitude heavier than our sun, collapsed down to an itty-bitty point. All that mass is still there. All the energy is still there. So let's do a quick calculation. Let's actually just, gotta keep our mathematical brains literate, keep practicing. And let's find how much, what's the event horizon if our sun was collapsed down to a black hole. So take the sun's mass, which is 1.9 times 10 to the 30th kilograms, and just grind out the calculation. Here's the Schwarzschild radius for a black hole that's the mass of our sun. It'll be 2 times the gravitational constant, 6.67, 10 to the 11th newtons meters squared per kilograms. Hope you guys can keep up with the units. Go back in sections. Check the units, right? Right, so there's big G, the universal gravitational constant. Here's the mass of the sun, 1.989, 10 to the 30th kilograms, and divided by the speed of light squared, 3 times 10 to the 8th meters per second, all that squared. And we'll find that the radius of our sun in order to become a black hole is about 3 kilometers. If you could take the sun's mass and compress it down to the size of probably your neighborhood, you'll have a black hole. One question that's constantly thrown out there, that spaghettification. What's happening? So remember we talked about tidal forces? How the moon and Earth are tidally locked to each other, and they have, because the gravitational force changes across the body, You get this stretching, this elongation. Well, same thing for a black hole. It's a very massive body. It's a huge gravitational force. And so what happens basically is that as you approach a black hole, even before you cross the event horizon, there's going to be extreme tidal forces. Basically, the force on your feet could be upwards of thousands of times stronger than the force on your head. And that becomes that stretching effect. So strong that it'll literally start stretching the atoms apart. Atomic bonds will be ripped away. Light will become redshifted in an infinite direction. Time dilation keeps going up. In fact, as you go towards more massive bodies, time dilation actually starts to increase. And so for you, things, an outside observer will see you slow down as you're slowly atomized apart. And that's what we call that death by spaghettification. Remember, this is concepts we studied before, just taken to the extreme. It's tidal forces, force on your feet versus the force on your head, on these extreme scales. Another crazy cool concept with black holes is the idea of Hawking radiation, named after the late Stephen Hawking. And he pointed out that, yes, black holes are these singular wells that if you cross event horizon, stuff gets trapped down there. But Stephen Hawking said there is a way for the energy of a black hole to be released. Nothing inside the black hole escapes. This is going to be some strange concepts. But nothing escapes out of a black hole. You fall down there, all of your mass, all of your energy just gets added to the mass and energy of the black hole. But what Stephen Hawking noticed is that there's a way for the net energy of the black hole to be reduced. So here's the process. You look at what's called the vacuum state. You say, in the vacuum state, there is still energy present when there's nothing there. And what can spontaneously happen is a particle-antiparticle pair are just generated in the vacuum state. Now, particle-antiparticle pair, energy from just the universe itself is forming two particles, and they'll slide around and annihilate each other. So energy is conserved in the universe. You didn't just spontaneously get free energy. It's just two particles spontaneously pulled themselves together from that energy and flew back together, just annihilating. So far away from black hole, this just happens all the time. Particle-antiparticle pairs just fly around, annihilates. So no energy's lost in the universe. But some of this happens around the edges of an event horizon. So what can happen is that you'll create your particle-antiparticle pair, and they're right on the edge of that event horizon. Well, if, say, the particle that has some net positive energy is over here, and the one that is net negative energy is down here, well, what happens? The net negative energy will contribute down to the black hole, whereas the net positive energy flies away, escapes. And so now we've seen a mechanism for how energy can eventually leave a black hole. You have this vacuum state particle-antiparticle pairs, and the negative energy just happens to be on one side of the event horizon, the positive energy on the other side. The negative energy will reduce the mass of the black hole, and the positive energy is radiated away. In essence, there is a stream of particles, the Hawking radiation, that's being radiated away from black holes, which has a couple of consequences. One, it means that black holes will not live forever. Even they, these huge gravitational wells where nothing can escape them, will eventually lose all of their energy. It's a strange process and long, but they do lose that energy. So I do need to talk about this vacuum state energy, because this does sound like just poof, magical existence of particles spontaneously creating themselves. But this actually is hard science. We've done experiments. One of them is called the Casimir effect. You basically take these plates, and vacuum fluctuations is creating this force between the plates. And so we actually have measured this. We have measured this idea of that vacuum state energy of particles being spontaneously created, destroyed, even in a vacuum. So going off of that, what that means is, let's put some numbers here to how long black holes live. Protons, neutrons, left alone, are probably some of the most stable things in the universe. The last proton will take somewhere of 10 to the 36 years to decay. I'm not going to try and put that in scale, because these numbers are so strange and different from what we can discuss. But to get an idea of scale of the universe, 10 to the 36 years for the final protons to start decaying. The black holes that still exist in the universe, they're going to be on the magnitude of 10 to the 67th years. So that's one with 67 zeros in front of it. That's how many years it will take for black holes to radiate all of their energy away and finally evaporate. So the universe is going to be around for a very, very long time. We've only been around for a couple trillion years, or billion years. We've only been around for a couple billion years. And this is billions upon billions and billions of years for the black holes to finally go away. So Hawking radiation will eventually cause a black hole to collapse, to lose all its energy. One way to sustain a black hole is to have a companion star. We see lots of binary star systems, and what can happen is one of those stars becomes a black hole, and it starts to siphon material off of its neighbor, and that will sustain itself, make it live for eons longer. But left alone, isolated, a black hole will evaporate, will eventually lose all of its energy. So, these next few slides, they used to say, can we detect a black hole? But now they have to say, how do we detect a black hole? And here's that very first image. This is from the supermassive black hole in M87. And this was captured by the Event Horizon Telescope. A lot of words here, so I want to spend these next few slides just talking about how did this image come about? What is it? How do we get this? And for starters, no, the fuzziness is not a glitch with your resolution. It's not an issue with your computer. That is the scale of the image that we've managed to capture. We'll talk about why it's fuzzy. And let's go through what's so special about this image, other than say it's the first black hole image. What did it take to get this image? So, here's the elliptical galaxy M87, Maser 87, right? And there is a supermassive black hole. That's the image that you just saw. Supermassive black hole at the center of that galaxy, right? That black hole has a mass of about 6.5 billion suns, which means that the event horizon of this black hole is 38 billion kilometers wide. Let's go back a bit. So, we have all of this orange material. That's not light, it's not photons going around. It's plasma. It's high energy, hot plasma circling around the black hole. The shadow here, that's the edge of the event horizon. Right? In here is where you've crossed the black hole and fall and so on. But this is your event horizon. The event horizon for M87 supermassive black hole is 38 billion kilometers wide. Put that on a scale. The orbit of Pluto is about 7 billion kilometers wide. So we need multiple Pluto orbits to define the radius of the event horizon of M87's massive black hole. So, this thing's very far away. Yes, it's big, which does help with trying to detect it. But how do we image it? How did the Event Horizon Telescope team actually get this image? Well, here's how it worked. They had, at the time, 8 ground-based telescopes working in unison. And they basically made what's called a giant interferometer. The idea is that you've got a telescope here, 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 all spread out across the globe. And by doing that, you get to build a supermassive telescope. In essence, the 8 telescopes are one gigantic super dish, all focused on the same object, M87. And by using interferometry and a ton of mathematical work, they're able to stitch together data from all these telescopes to get that image of the black hole. So why is it fuzzy? Why is it blurry? Well, in terms of angular size, M87 is about 50 micro arc seconds in angular size. And what does that mean? Imagine you live in New York and you pulled out your telescope and looked all the way to Los Angeles and then started counting dimples on the golf ball. That's about the same angular size that the Event Horizon Telescope team tried to measure. Across the continental United States, counting dimples on a golf ball. So, yes, there's tons of work and improvement. More satellites, as more telescopes join in on the Event Horizon Telescope team, the clearer, the crisper these images of these black holes of other galaxies are going to start becoming. So let's wrap up. We said that, hey, it takes infinite energy to move something with mass at the speed of light. And when you're moving at relativistic speeds, classical mechanics starts to completely fail. And you need to start talking about things of like length contraction and time dilation. The fast-moving objects are going to be literally seeing a squished universe. And time's going to go much slower for them. And we have more than a century's worth of experiments now, to confirm relativity. So I'll leave you on this image of this gravitational micro-lensing of lights. Another example of relativity bending the path of light rays. We'll call it an end there. Take care.